Hello everyone, welcome back to iTeach Physics. We are continuing with the gas laws. We did Boyle's law last time. You can check that video out. I will leave a link at the top. Today we will be looking at Charles' law. Now Charles' law states that volume is directly proportional to absolute temperature. This is temperature in Kelvin at constant pressure. The expression would be V is directly proportional to T, volume, to temperature at constant pressure. Now we can actually write an equation. Volume is equal to some constant times absolute temperature. Therefore, this constant is equal to volume divided by temperature. The temperature is the independent quantity and the volume the dependent, since the gases will occupy no new volume without an increase in energy. If the container was stretched, then the pressure will not be constant. So we're going to look at this in a short while. Here is a graph of volume against temperature. Now what this is saying here is that if you have a container with gas, the gas will not occupy any new volume on its own. There needs to be some increase in energy, thus an increase in temperature also, that causes this gas to now occupy a new volume. The other case would be to stretch the container, and in stretching the container you would not be keeping the pressure constant. So let us now look at a simulation. So here I have this simulation. What I am going to do, I'm going to adjust the volume of this container to start us off. I believe this volume is a little too big. So let's see what happens. Please remember that pressure is due to the particles, the gas particles colliding with the surface, the inner surface of the containers. Therefore, we can actually count those collisions using a counter. So every 5 picoseconds, we will notice the amount of collisions, the average collisions that happen. You can take a look at the pressure reading over here and also the collisions. I believe it's much easier to look at the collisions since the pressure reading the average remains the same. Now what we want to do is keep this pressure now constant, and let us apply some heat which will change the temperature of the container. What you see happening is the particles, they get more energy. Therefore, they are going to start hitting into the walls of the container more often. And in order to keep the pressure constant, keep the amount of times or the rate they hit into the container constant, the volume that they have to travel needs to increase. So this is why if you increase temperature, then the volume has to increase also in order to keep the pressure constant. So they basically compensate for each other. The volume will compensate for the temperature. Now using more particles, we see the same thing happening. You give them more energy, you increase the temperature, then they need more space in order to move around and hit in the walls of the container at the same rate. If we decrease the temperature, we know that they're going to get a lot slower. So we need to decrease the volume inside of the container so that they hit into the walls at the same rate once again. So I hope this simulation was helpful. You can replay this part of the video if you'd like. Let's move on to some questions now. Now here we have a question. It says a sample of helium gas has a volume of 521 dm cube or decimeter cube at a pressure of 650 millimeters of mercury and a temperature of 18 degrees Celsius. When the temperature is increased to 23 degrees Celsius, what is the volume of the helium? Now let us see. So we have two scenarios. One in which the temperature of the gas was at 18 degrees Celsius and another where it has risen to 23 degrees Celsius. We want to actually find the volume at the new temperature. So scenario 1, we say the volume is 521 dm cube. Remember, we are dealing with ideal gases. We are looking at the gas laws. If we have a temperature in degrees Celsius, we will want to change it to the absolute temperature. So what we do, changing degrees Celsius to Kelvin, we add 273.15 to our Celsius reading. So our initial temperature is therefore 291.15 Kelvin. Scenario 2. Scenario 2, we have the new temperature 23 degrees Celsius converted to Kelvin, 296.15 Kelvin. But what we don't know is our second volume. Since we know that some constant K is equal to volume divided by temperature, therefore we can say in the first instance, K is equal to V1 divided by T1, which is our first volume, divided by our initial temperature. Now in the second instance, we expect to get the same value for K because the amount of gas we are working with is constant. It doesn't change. It's the same mass. And so we can say K will be the same in both instances. So what we have happening here, K is equal to it's a ratio of the volume to the temperature. Now this ratio will remain the same. However, our temperature changes, so our volume must compensate. So since K in both instances are equal, we can equate V1 over T1 to be equal to V2 over T2. Now let's see what that gives us. From the equation we have set out, we can make V2 the subject of the formula, and now from there it's smooth sailing and we get V2 to be equal to 530 dm cube. Therefore, our observation holds true even in the calculation. Where there is an increase in temperature, there will be an increase in volume once pressure remains constant. Please stay tuned for our next video. It will be on the pressure law or Guy-Lussac's law.